This video is going to focus on 3D solids, solids of rotation. So 3D solids formed from rotating 2D shapes around an axis, and cross sections, which are slices of 3D solids. So to get started, a solid of rotation is when we take a 2D solid and we rotate it or spin it really fast around an axis so that it becomes a three-dimensional solid. In order to see this happen, I have a link over here. Let me open it up. And let's take a look at a triangle. If we take a triangle and we rotate it really fast around an axis, this link is going to let us see what 3D solid it's going to become. And look at that, it becomes a cone. If we take a look at a rectangle and we spin it really, really fast, I'll do that one more time, it becomes a cylinder. And if we take a circle and we spin it around an axis of rotation, look at that, it becomes a sphere. Those are three of the most common solids of rotations that you're going to see. So anytime you have a triangle and it's rotated around an axis of rotation, it is going to become a cone. Anytime you have a rectangle and you rotate it around an axis of rotation, it is going to become a cylinder. And anytime you have a circle and you rotate it around an axis of rotation, it is going to become a sphere. Moving on to the next part. Sometimes it could be a little bit tricky to visualize what 3D solids are going to result after rotating a 2D shape. So if we take a look below, notice how in all of these images, they're all rectangles. So as we saw in the GeoGebra link before, they're all going to result in cylinders. But depending on where the axis of rotation is or how the axis of rotation is oriented, whether it's vertical or horizontal, we're going to get different looking cylinders. So if we take a look at this first example over here, if I take the vertical standing rectangle that's shown and I rotate it really, really fast about the axis of rotation, which is that black line that's shown, I'm going to see a cylinder because it's spinning really, really fast around the line. So I'm going to see the same rectangle appear on the other side because it's going to spin really, really fast. I'll just shade it in. And I'm a really horrible artist, but I'll just make these parts look curved over here. And there we have a cylinder. It's going to be standing up tall, and that's what it's going to look like. Moving on to this one over here. Notice that there's a difference between this one and the one that we just looked at. And the difference is that even though the rectangle looks the same, the axis of rotation is in a different spot. It's not right up against the rectangle. There is a gap in between the axis of rotation and the rectangle. And I'm a horrible artist. But what that means is when we spin the rectangle really, really fast around, we're going to see it over here. So what that means is that we're going to have a hole in our cylinder. So we're going to have a large cylinder, but since we have that gap between the original rectangle and the axis of rotation, we're going to have a hole in the middle of the cylinder. There's going to be a hollow part in the cylinder. And if we take a look at this last one over here, notice that the same thing's going to happen because there is a gap between the rectangle and the axis of rotation. Also, the axis of rotation here is horizontal, so the entire cylinder is going to be oriented differently. It's not going to be standing up tall vertically like it was in the previous ones. It is going to be laying on its side when we rotate it around. So it's going to come off the grid a little bit, so not, completely drawn to scale. Oh, I should use blue like I was using before. And we're going to see the rectangle on this side. We're going to have a cylinder. Once again, I'm a really horrible artist. and there's going to be a hole in the middle. There's going to be a hollow part in the middle. But notice how the cylinder is laying on its side because of how we were spinning it around a horizontal axis of rotation. So it's a good idea to draw out, even if you're a bad artist like me, to draw out the result so that way you can see the orientation of the resulting solid, and that's going to help you answer questions. For these questions, you should pause the video, read the question, and then unpause to see the answer. So on this one, we have a flag spinning around a flagpole on a windy day. And it's asking what shape would the spinning flag create. And since it's a triangle, we're going to see it on both sides. And the straight edges are going to look curved. And we have a cone. And as we said before, and as we wrote down earlier in the video, a triangle is always going to become a cone. Here we don't have a full circle being rotated around the y-axis. Here we have a quarter of a circle. So instead of seeing a full sphere, what we're going to see is a part of a sphere. When we rotate it around and we see it on both sides, it's going to look like this. Once again, I'm a horrible artist, but it's not a full sphere. It is a half of a sphere or a hemisphere, and that's what we get. Here we're rotating around side W. So we're going to see it on both sides. The straight edges are going to look curved. And here we have a cylinder. In the next one, we're rotating triangle RST around leg RS, around this leg. So we're going to see it on both sides of that leg. And I should probably put the curved part over here. And we have a cone. For the next one, we have square math. And each of the sides have a length of 7. And we are rotating around side AT. So here's side AT on mine. So I'm going to see it on both sides. Straight edges are going to become curved. And I have a cylinder. And it's a right cylinder because it's standing up straight. And the radius is 7. The whole way across, the diameter, the whole way across the circular part would be 14. The 7's halfway across. So that is going to be a base radius of 7. In the next one, we have a rectangle. And the rectangle is 6 inches long and 5 inches wide. And it's going to be rotated around the longer side. So here's the longer side. So we're going to see it on both sides. And what's resulting is a cylinder with a radius of 5 and a height of 6. So always draw it out. It makes it a lot easier to see. And then over here, we are rotating triangle ABC around side BC. So side BC is over here. So we're going to see it on both sides. And it's going to look like this. So that knocks 1 and 2 out. So always draw it so you can see how it's oriented. And one has a diameter of 5. One has a diameter of 10. The diameter here is 3, 4, 5, 10. So we have our answer. Next, we're going to talk a little bit about cross sections. A cross-section is a 2D slice of a 3D solid. So if you imagine that you are just slicing a solid and seeing what shape you pull out when you make that slice. We can slice parallel to the base, which is horizontally if the solid is right side up. Or we can slice perpendicular to the base, which is vertically if the solid is right side up. You can also slice diagonally and get different shapes. But most of the time you'll see parallel to the base and perpendicular to the base. And let's see, get a better idea of what cross-sections are by seeing some cross-sections in some 3D solids. So first, I'm going to show you with a cone. So here we have a plane that is parallel to the base, that is intersecting the cone, so parallel to the base, not intersecting the base. And notice how the resulting shape is a circle. And if I move up and down horizontally, parallel to the base, horizontally, notice that it's still a circle. The circles do get bigger and smaller, but it's a circle. If I tilt so that I'm perpendicular to the base, I get triangles. And then if I tilt so that I'm diagonally, I get some other interesting shapes over here. Let's take a look at what cross sections can result from a cube. So if I slice a cube parallel to the base, I'm going to get squares. And that makes sense because the bases are squares. And if I cut perpendicular to the base, I'm going to get squares as well. That makes sense because the faces are all squares. And if I slice any way slanted, any way diagonally, I'm still going to get a square as well. Wow. Let's check out a rectangular prism. A little bit different than a cube because a cube is made up of squares, rectangular prism is made up of rectangles, right? So rectangles have a different length and a different width. So the slider's working now. So parallel to the base, we're going to get rectangles, the same rectangle. And that makes sense because the bases are rectangles. And if I do a vertical cross section, it's going to be a rectangle as well. And that makes sense because the faces are rectangles. Oops. I didn't want to drag that slider. I want to go to this one. And if I cut diagonally, it's going to result in rectangles as well. Those two weren't so interesting. Oops. Let's check out a cylinder. A cylinder is going to have a little bit more interesting results if my iPad will allow us to click on it. Okay. First, we're going to cut parallel to the base. And notice that we get the same circle. It's a constant cross section, no matter where we go parallel to the base. And I'm going to go perpendicular to the base next. And notice how I get a rectangle when I'm perpendicular to the base. And then I want to go diagonal. And I get these ovals when I go diagonal. We call those ovals ellipses. That means they're not completely circular. So I can get ellipses as well out of a cylinder. And then finally, the last one that we're going to take a look at on this video, and it's the last common one that you are going to see, is going to be the pyramid. Sorry for the back and forth with all these links. It's hard to visualize cross sections without taking a look at a visual sometimes. And here we're going to start off with parallel to the base. And notice how parallel to the base, this is a square pyramid, so we have a square, the same as the base. The squares change in size, but it's still a square. If I do perpendicular to the base, I get a triangle, the same as the faces. And if I do a slanted cross-section diagonal, I do get a trapezoid. So that's an interesting one as well, that you can get a trapezoid from a pyramid. We're going to end with some Regents questions so we can see what Regents questions on this topic look like. So here's the first one, and I recommend that you read the question, pause the video, and then unpause it when you're ready to see the answer. So which figure can have a triangle as a two-dimensional cross-section? Well, we just saw cubes only have squares. We did see that a cone can have a triangular cross-section when we were slicing it, when it was right side up, when we were slicing it perpendicular to the base. The same as the faces around it kind of are triangular. That was perpendicular to the base. And the square pyramid definitely had triangles. Let's check back and see the cylinder. The cylinder I don't think we got from. So cone and square pyramid. Taking a look over here at number 2, Oh, so there's an error in these answer choices. One should say 1 and 4 only. So I'm going to make my own 1 and 5. 1 and 4 only. And that would be the answer. Okay, we have a right hexagonal prism, and we're slicing perpendicular to the base. So that's going to be the same as the faces, which is going to be a rectangle. If the question had said parallel to the base, it would have been the same as the bases, and it would have been a hexagon. Which figure can have the same cross-section as a sphere? The cone has a circular base, so if you slice parallel to the base, you can get a circular cross-section, which is the same as a sphere. The cross-sections of a sphere are circles, as you might have guessed. Here we have another one about a hexagonal prism, perpendicular to the base. So we have a nice picture of it over here, which would result in the same answer, a rectangle. If it was parallel to the base, once again, it would have been a hexagon.